Alright, we are live. It's a couple minutes early, but people can rewind to get to what they missed. Alright, which of the phase relationships below is true for a series LCR circuit? So this is a series circuit with inductance, capacitance, and resistance. So let me just go ahead and draw that out. This is the stuff from some of the last stuff from the last video. But all delete. Oh look, I can. Okay. So I've been drawing triangles for everything for you guys so far, and it's gonna be some more triangles. Okay, so we got this. Let us use some lines just so it looks a little bit neater. A little bit longer. Alright, and then come out here. Oh. That's close enough. Okay. So up here we have x of L. This is 90 degrees. This is 90 degrees. R, N, X, C. These are vectors. So they act like vectors. If you are familiar with vectors, which we did some lessons on vectors, what, 6 months ago? So that should be very fresh in your memory. Alright, which of the phase relationships below is true for a series LCR circuit? EL and EC are 90. Okay, so this is all about the voltage triangle, not the resistance triangle, which is, it's the same. Except is voltage instead of, so it's E of L, E of C, and E of R. And this would be E total, and this will be Z. Now, if you have the other one, it would be down here. X of L and X of C subtract from each other, so whichever one is bigger will be the direction that it goes, that Z goes. Okay, so knowing this, E of L and E of C are 180 degrees away from each other. E of L, ER is 90 degrees. EC and ER are 90 degrees. And all of their relationships with E total depends on what the numbers are. EL and EC are 90 degrees out of phase. That is wrong. EL and EC are 180 degrees. Yes. EC leads the current by 90. No. EL lags the current by 90. So, to explain that, in a series circuit, I is there. It's just all of the currents are at 0 degrees. E of R is at 0 degrees. So EC is at negative 90 degrees and EL is at 90 degrees. So EL leads current by 90 degrees. EC lags current by 90 degrees, which I believe is the opposite of what this question is. Yes. So the only one that is true is B. So phase relationships is true for a series LCR circuit. So that would have to be D, because all of the currents are at 0 degrees, right? So IL is at 0 and EL is at 90. So IL is 90 degrees behind EL, so it's lagging by 90 degrees. Oh, nobody put that one. Everybody was like, nah, that can't be it. These first two cannot be true because IL and IC are both at 0 degrees because current stays the same in a series circuit. So IL and IC are at 0 degrees. So they are identical. IC lags the voltage by 90. And that's just not true. IC is at 0 and EC is at negative 90. So IC will lead by 90. Remember. And then Eli and ICE. In an inductive circuit, which is L, voltage leads current, and current lags voltage. That's. And then in the capacitive portion, current leads voltage or voltage lags current, depending on which way you want to look at it, or which way the question is looking at it. So pay attention when you are answering these questions. What is the true power in the circuit in the figure below? Given R equals 350 ohms, E applied is 24 volts, which is going to be your total voltage, is 24 volts. Z equals 500 ohms, and I total is 48 milliamps. Wow, they just gave you everything you needed. Alright. So let's make out our chart. It's going to be a super easy one. No, that picture doesn't really give us anything. So let's make our chart out. So we need a brush. We need Z equals, it was 500 ohms, I want to say. Yes. I total is 48 milliamps. E applied is 24 volts. So they didn't give us apparent power yet, but that's a simple matter of multiplication. Also, it's not what they're asking for. So, and then we need R is 350. We know I of R is 48 milliamps because it's a series circuit, and that hasn't changed. E of R, we have no clue right now, and P true. So the crux of this question is knowing that true power is the power that has to do with resistance. Do we care what X of L and X of C are? No. We actually don't have a way to find what they are as far as I can tell. We can know more about them, but we can't find specifically what they are. Since they cancel each other out, they could be almost any number individually, as long as their difference is whatever we find. So we're going to ignore it. We're going to ignore that part of it. We're just going to, so now that we're just going to solve our chart. Now that we have our chart, and remember 48 milliamps, you move the decimal 3 times, that's going to be 0.48 amps. So let's go ahead and multiply across to get our true power, because that's all we need to do is work with when you put a straight edge on it, I kind of do not do a good job. We're only working with this row. Here, I'll just put the line underneath. Yeah. Alright, so all we have to do is 350 times 0.48 gives us, it's 0.048. My bad. One, two, three. Got in a hurry. So that would be 16.8. But let's do the math again. 350 times 0.048, 16.8. What cued me off is that your voltage shouldn't be higher than what you started with. And I had 168 volts showing, which is clearly wrong. Okay. 16.8 volts. And then we just rinse and repeat. I of R times E of R will give us true power. 0.048 times 16.8, 0.806. And that will be measured in watts. That could be 806 milliwatts. Let's see what we got. 806 milliwatts. There it is. All right. What is the applied voltage of the circuit in the figure below? Given R equals 24 ohms, I total is 6 amps, X of C is, what's the applied voltage? Okay, so they're actually asking you to do something here. So let's go back here. Let's select. Let's clear out the old stuff. Make room for the new stuff. We won't care about powers in this one. We've got I of L and I of C, E of L, which we won't get to any of this. E of C. We can now in this one. then maybe I'll work out the full thing. So I'm gonna draw out your triangle, or it's not a triangle at this point, it's like a T, but 24, 80, and 48. So your formula for finding Z in a circuit that has X of L and X of C. So in a circuit that just has one or the other, it's just simply Pythagorean theorem. So it's Z equals, and you can use this for whatever set of them. Z equals R squared plus XL squared. Or it's Z equals square root of R squared plus XC squared. When you have both of them, it's Z equals square root of R squared plus XL minus XC squared. They cancel each other out, and you have to subtract them before you can do anything. They have, so they are vectors. They're going opposite each other. So this is XL, which is 48 ohms, and this will be XC, which is 80 ohms. You subtract them and you get a vector. Let's just do that real quick. 48. It doesn't matter which one you subtract from the other, because you are squaring it. I usually just go ahead and subtract the bigger, or the smaller from the bigger, so I actually have a positive number. It's a little bit more straightforward to me. So 32. So you get a, and we will have a 24. Let's do, and then our resultant vector will be here, and it'll be 32 ohms. And we need to find Z. Well, in this case, we've already done the X of L minus XC. We got 32. So we just need to do Z equals the square root of 24 squared, which is our resistance, plus 32 squared, which is our X of L minus XC. Oh, I closed out my calculator. Hang on. Alright, calculator's back. Let's drag it up here. So open parentheses, 32 squared plus, oh, it doesn't matter what order it's in. 24 squared, close parentheses, and then take the square root of that. Z equals 40. So since Z equals 40, now I need to write down the other parts. I total is 6. So this was given to you in the question, 6 amps. Well, all we're caring about is this top row, because we're trying to get applied power. How much voltage, I say applied voltage. How much voltage was applied to the circuit? So 40 times 6, that's 240 volts. And that's it. That's all you had to do. It's this was a fairly simple one. You can see that it's mostly about knowing. There's nothing expressly difficult about this, but knowing where to do what math is the difficult part. Knowing the x of L and xc subtract from each other, and then it's just a triangle and you find the hypotenuse, then it's Ohm's law. All we've really added in this set of things is that x of L and xc subtract from each other, and then you do the hypotenuse. 240 volts. Hey, at least this time the correct answer was the most chosen answer. Barely. Like by one person. Alright. Okay, this one should be a very simple one. Which circuit below does not show a resistor connected in parallel with an inductor? So, this symbol right here is an inductor. This symbol is a resistor. These two are in parallel with each other. These two are in parallel with each other. You can see the current splits and goes to both of them. Any current that goes through this resistor has to go through the inductor, and then through that resistor. There's no parallel resistors in circuit D. So circuit D is the answer. Good job. Good job, everybody. Pat yourself on the back. If the frequency is increased in a parallel RL circuit, the phase angle will decrease. Parallel RL circuit. So, this is... Oh, that was the beginning of parallel. Okay, so we are moving from series to parallel now. So the next 3 lessons are parallel lessons. Okay, so it's going to be so there is no longer a triangle for impedance. Like, that does not apply. There is a formula for impedance in your book. It's unnecessary and complicated. I don't recommend using it. You are welcome to look up your book and look it up in the book. But I am not going to go over it because it's unnecessary and complicated. It also only works under specific circumstances, and I don't like teaching things that only work under specific circumstances. If the frequency is increased in a parallel RL circuit, the phase angle will what? So, things that still apply in parallel. X of L equals 2 pi FL. So, if frequency is increased, F goes up and X of L goes up. What do you remember about how resistance works or not how really resistance works, but how voltage goes on parallel legs? Really we're talking about power, but voltage too, or current, power. We're talking about power. We're talking about how power works in parallel. So, in a parallel circuit, this is the circuit we're talking about. If they're both equal, so 10 ohms and 10 ohms, they're going to have the same amount of power. So, let's say 10 watts. We're just going to make everything super easy. 10 watts. Then, if you increase frequency and X of L goes up, well, resistance isn't going to change. X of L goes up, let's say it goes up to 20 ohms. Well, now it's harder to get through this leg, so less current is going to go down that leg. This is the equivalent in the grocery store where you get in the line at the grocery store and then you look forward and they just changed cashiers and it's a slower cashier. Less people are going to start getting in that line. So it goes up to 20 ohms, and this, since the resistance doubled, the wattage is going to cut in half. And I'm not going to get all the way into this, but we'll say it cuts in half. 5 watts. That's probably not actually how it would work specifically, but it's going to go down. The wattage here is going to go down. But all that extra is going to go down this lane now. We'll get into actual numbers, but this is just some simple numbers to make the point. So you're having more true power. P true goes up. If you increase frequency, true power is going to go up because there's going to be less power going on the reactive side. And if apparent power stayed the same, then your power factor got better. Power factor getting better means this angle, a better power factor means this phase angle got smaller. So remember that up and down the vertical line that I'm increasing and decreasing right now, that's that 5 watts. It went from 10 to 5. From 10 to 5. And let's say the true power didn't change at all, but it went from the apparent power went from 10 to 5. Well, now you have the same true power and probably more, or it's probably slightly less apparent power, but still this phase angle got better. So let's go back to the question. I don't remember what it was. If the frequency is increased in a parallel RL, sorry, the phase angle will. So if you increase frequency in parallel RL, the phase angle will decrease. But this is only parallel. It would do the opposite in a series. But in parallel, it's going to decrease. Was the true power for a circuit with applied voltage of 48 volts, a current draw of 33 amps, and a power factor of 94.7%. Okay, so what this is saying, so let's pull out our calculator. It's got 480 total volts and 33 total amps. So the total power is 15,840. Okay? And 94.7% of that power is the true power. That's what power factor is. That's the percentage of the total power that is true power. And then the rest is wasted power. So all you have to do once you get this 15,840 is multiply it by 0.947, because that's 94.7%. And that's how you get the percentage of something. So that's 15,000. So 15 kilowatts, because kilo means 1,000. All right, that's it. And that's the majority. Good job. I feel like some of you I mean, I looked at the results table. A few of you just straight up hit A all the way across. I see that. I see what happens. Which figure below correctly shows the phase relationships between the current and voltage in a parallel RL circuit? Parallel RL circuit. Well, we know E of R. Well, okay, in parallel, voltage stays the same. So voltage has a 0 degree. Voltage is 0 degrees. Voltage leads current. So voltage will be 90 degrees ahead of inductive current. So ER and IR are at 0 degrees. Yes, absolutely. ER, IR. So we're between figure A and B. Voltage leads inductive current in a parallel, or voltage leads current in an inductive circuit. So voltage is, if voltage is at 0, current has to be at negative 90 degrees. Because voltage is 90 degrees ahead. And in parallel, voltage is at 0 degrees. So IL is at negative 90. So figure C is our correct figure. Figure A is the closest other answer. These others are just completely wrong. Everything having to do with resistance is always at 0 degrees. And then IL is at negative 90 degrees. So that's what gives us this C. All right, let me start the new quiz. Need to check. Looks like I don't remember who that is. I'll have to check the roll again. Alright, AC Theory 2, 5, and 6. Alright, this is a little bit longer one. It is 11 questions. So good luck with that, guys. And I will see you guys in a few hours.